morning, everyone. So, mine is the last presentation of this session, so probably the last presentation of this conference. So, thank you. I'm going to talk. My name is Dhananjay Srivastava. I'm a professor, associate professor, Department of Mechanical Engineering in IIT Kharagpur. So, my talk is related with advanced valve actuation system. So, I'm agree with the first our presenter that when we are talking about the engine, then along with the fuel, we need to talk about the engine hardware, engine technology also. That still has a potential to improve the efficiency of the engine. And from that point of view, that is what I'm going to take it forward. So if you look the internal combustion engine, there are several ways that we can improve the efficiency or the of the engine. There are various alternative fuels that has been already discussed in these things. There is hardware modifications. There are several concepts of the combustions as well as the control systems. So in one of the, if you look very carefully of the engine, we need to think. The things is that which one is the laser power counter? Oh, that's right. So in the SI engine, we have a throttle. The main function of the throttle is to control the airflow rate. But do we need to think that at this present moment, do we need whether the throttle of the SI engine is the part, is it the necessary? Why not till now we have come out from this throttle part? Because we know that because of the throttling, we have a throttling, less pressure in the downstream of the throttle. And because of that, here the manifold pressure is very low. It can vary depending upon the throttle positions. It can vary from 0.3 bar to the 0.8 bar. And because of the low load conditions, piston has to do the extra work in order to draw the air or air fuel mixture in the intake stroke. And then similarly, so because of this throttling, what is happening that we have a problem. So the questions, and if you look the fundamental of our Otto cycles, that obviously it is not going to be the atmospheric pressure. The low intake is going to happen at the lower pressure, and the exhaust is going to happen at the above the exhaust pressure, atmospheric pressure. And so this pumping loss, this is the negative loss. How we can change this negative or eliminate, or most of this energy can be transferred from the negative work done to the positive work done. So the questions comes in our mind that is it possible to eliminate the throttle from the SI engine? The second things that also comes in the mind that whenever we see the power output or the torque power output of the engine, then you find it out that this is the power output at the particular engine speeds or in the particular very short range of the speeds. Then the questions comes in our mind that why the power or torque output is coming in a very short range of the power output. For the example, this top torque maximum torque output can be the flattened curve. We can get it. Ideally, obviously, it's very difficult, very difficult practically to get it in the rectangular shape of the curve. But can we flatten or we can wide the range of the engine speed where we can get the maximum torque output? So these are another fundamental comes in our mind that so the second question arises how we can widen the range of the speeds at which we can get the maximum torque output. The third point is that we have a valve actuation that plays the important role in order to do the gas exchange process. So and this valve is governed by the camshaft. Mostly we have overhead camshafts. But what is the problem with this conventional valve actuation system is that valve events, like for example opening and closing and the valve lift or the valve durations is the fixed irrespective of the engine speeds. It is fixed for an engine. So the questions comes that that the valve events regarding this valve opening, closing, or the valve lift, or the valve duration, is it the independent parameter with respect to the speeds? If yes, then it's very good. This technology is working very fine. If not, then how we can tweak this kind of the constraints that still exist, and we can get it for the more power output. So this is the conventional also. So we have three questions in our mind: how we can remove the throttle. The second question is how we are widening the range of the speeds, and the third question is it the valve events is independent of the engine speeds or not. If you look very carefully, this is the typical valve timing diagram that we are getting it, but when we will look very carefully, then what we are getting it, at the lower speeds of the engine, we need to do the IVO very close to the top dead center. Wherever we need to do the IVO at the high speeds is much before the top dead centers, because at the lower speeds, if the IVO is going to be taken place even much before the top dead centers, the backflow is going to be taken place. So if you analyze the valve opening and the gas exchange process, what we will find it out that the valve opening and closing at least has a requirement of the different, it's a completely opposite in directions at the lower speeds and at the higher speeds, and it varies with the speeds in between that. So how we are going to achieve that? So that is true that the current valve diagram is not the optimized one. It is just the sandwich between the low speed and the high speeds, and that is the reason that we are going. Our valve timing diagram right now is fixed, or it is optimized at around 2000 to 3000 RPM of the speeds, and that is the reason that we get the maximum volumetric efficiency and we get the maximum torque output only within that range of the speeds. So how we are going to do that? Okay, this is the same things, it is summarized here. So okay, these are already discussed. So the things is that obviously the current OEM automotive manufacturers, so they are not just following the fixed valve timing diagram. They are providing, now we have a certain technology in the market, that is cam based variable valve actuation systems is working. For example of the cam switching systems, where at least we can have two valves or two loops on the same cam shaft, where we can get the optimized conditions for the lower speeds and the higher speeds, but it is also in the discrete in nature. We have a cam phasing, we can change the cam phasing between the cam shaft and the crankshaft, and in that way we can change the valve opening and closing. But all these technologies, whatever the mechanical based valve actuation systems we have, we are getting at least much better than our conventional valve actuation system, but still it is a discrete in nature. It is not the continuous systems. We need so what we are working right now, we have already proven the concepts, and we are working in the next phase, that we are trying to develop a camless engine, that we don't have a cam, where the valves is going to be actuated with the help of some other systems. So these are the three technology we have, like for the electromagnetic, right, electrohydraulic or electropneumatic systems. All these three methods, whatever we have to actuate the valves, it has all pro and cons. It depends upon the thorough investigations of all these three methods, that which one is going to be the best suitable in terms of the energy input and the energy output conditions. So initially we have started, in fact I would not say some of the research is still going on. In Swedish, one of the universities is very aggressively working on such kind of the camless engines. In fact, one of the companies also claiming that they have in fact developed the production grade camless systems also. So right now we started with the electro-pneumatic systems. So yeah, this is the one of the free valve a company that is in the Sweden that has developed about the camless systems, and they are providing their OEM for the final production engine. So we will have with using the camless systems, we will have the variable valve durations. We can change the valve timings. We can have the variable lifts also, and then we can have the variable valve timing also. That is the possible to get it. So this systems has some of the advantages that since we are going to remove the camshaft, timing belts, throttles, and all these things, it is going to be the comparatively lighter. Since we have a direct control on the valves, we can have the variable compression ratio, but just by changing the playing with the IVU and EVC. Then we have the fast burning rate, because we can create the turbulence at the lower, even at the lower speed, just by lowering the valve lift, because we don't need the full valve lift. If the valve lift is less, then you can create the turbulence even at the lower speeds, and that may enhance the combustions also. So okay. So with that information, we started with our journey, and we developed first of all this offline testing of the technology, in which here we have the pistons, actuators. We have a pistons, and it is two ports, of port A and port B. Both port is connected with the two solenoids, and that the mainly thing is connected with the compressed wire. By controlling the solenoids with the help of the microcontrollers and opening at S1, S2, S3, 4, we will able to get, this is our things, and this is the valve that is connected here. So we first of all try to do the fundamental analysis that how much pressure is required, what should be the opening and closing durations of the valve actuators to get our desired valve lift, valve durations. In that way, we started with that. We do the one of the, I think no doubt about that, that we can characterize such kind of the things by using the positioning sensors like that, or even with the high speed camera. So we use the high speed photographic methodology to track the valves, and then we do these things. So how we have got the backward and forward motions of the valves. So when we need to have forward motions, we are going to pressurize the upper chamber and decompress the lower chamber. Then we are going to the forward motions, and vice versa. We are going to get the backward directions. It is possible that if we can play with the opening and closing of the solenoids, we can get the part lift off also, and in that way we are able to achieve the different valve lifts with playing with the timings. And when we do the multi-cycle analysis also, what we can get, the valve lifts has a COV of less than 0.08%. But one of the most critical things when we are developing the camless engine is the seating velocity of the valves, because here the valve is going to hit the piston heads at very high speeds, then its material integrity of the cylinder head is going to be compromised. So this velocity is not acceptable. We know that what should be the, because when we can find out the conventional valve actuation systems, and then we know that. So this velocity is not going to be acceptable. It is going to destroy the piston head, cylinder head. So we try to first of all create some kind of the cushions kind of the facility here. We give some of the pressurized air during the forward motion in the backward directions also, and try to not let it hit the pistons at the top dead center or the bottom dead center, and then in that way we try to play with that, and from the 1.28 meter per second, the seating velocity has been decreased to 0.38 meter per second, and that is achievable, and it is within the limit of the seating velocity. Seating velocity is very critical factors when we are developing the camless engine. Then after this testing, to prove the concepts, we also integrated the whole systems with the single cylinder engine, and then we did some very experiments, and we were able to save the BSFC at around 12% at the low load conditions. just to by reducing something around 60 to 65% of the pumping loss, and control the airflow rate with the opening and closing and the durations and the valve lifts. And tested since there are some limitations with the solenoid valves, so that this technology has been tested maximum up to 1600 degrees and 1600 RPM only. So this is our the proof of concepts. Now we are working on the next phase of that part, where we can extend the range of the RPM with the advanced solenoid based systems. And also initially we played with the pneumatic systems. What we come that compressing and decompressing of air is a bit difficult. We are trying to utilize the mixed technology of the electro-hydraulic pneumatic systems, where we can have the better control at the part load condition, part lift conditions. Obviously, this technology has a lot of problems and challenges also. That is what one of the seating velocity that we have to be very careful, that we have already discussed. In the part lift, one of the challenges is the holding of the lift in a stable conditions accurately. The robustness, it has to be the cost and packaging and all these things. And in all these discussions, one question comes in the mind that we are dealing with the pressurized air, where from we are getting the pressurized air. So another concept where what we are thinking about that as one of the author has told, that we are wasting the energy, lot of the energy in the exhaust gas, since very few SI engine is a turbocharged engine. So can we utilize the turbocharged conditions and have a very small reservoir of the compressed air on board itself? Our aim is to develop this technology with the maximum pressurized air with less than the 3 bar, and that if it is possible, we cannot going to get the fill up the pressurized air. It is possible to get it with the energy of the exhaust, fill the reservoir for the time being, and then we can have. So that with this aim, we are trying to develop it. Hopefully, we will do in the coming 2-3 years. Thank you.
So we can have questions for you.
I have a question and a very nice presentation. You said to reduce the wall seating velocity from 1.8 to 0.38 meter per second, I think you are sending the air in the bottom also. So this may lead to repercussion, that is wall can move up also because of this. How to overcome this?
So that is why this is when we are going to develop with the pneumatic systems. Okay, this is the one of the biggest problem with the holding the valves, or even the controlling the seating velocities and having no any fluctuations at that end point. If you are going to play with the air gaseous medium, it's going to have a demerit. That's what we come to know that when we are developed at the end of this technology, and that's why the second page we are trying to maintain with this kind of the flexibility with the hydraulic systems. So it is going to be the combination of the hydraulic plus the pneumatic, where the initiations of the valves is going to be the help of the pneumatic systems, but the holding it at the proper positions or at the lower level, it is going to control with the hydraulic systems. That is, it is to maintain the pressures very accurately. So that is what our going to be the second steps. That is the combinations of the electro-hydraulic pneumatic system.
Definitely damping will be better when you replace air with oil, but still there will be
that is even with the COV of the with the air, we have achieved the COV with the multi-cycle analysis was less than 0.03%. So in the hydraulic system, the system is going to be improved even much better. That all depends upon the your designs and how the flow of the these things is going on. So it's possible, but we believe that it is possible, and system is going to be more. It is going to be improved, in particularly with this problem when we are going to play with the hydraulic systems also.
So are you what to say that? Are you trying to develop the same prototypes for the engine application?
Yes.
With the same number of solenoids and
No, this is what I represented here during our first version of the technology, where we have used so many solenoids and everything. now what our next phase is that it's very close to the realistic conditions where the packaging and everything within it's possible, because this is our just first proof the concept. So we are now.
You need to consider the engine speed also. As the speed increases, the valve actuation time, the cycle time changes.
That we are taking care. That we are taking care that even though if the engine speed is going to be run at 4,500 or 5,000 RPM, so how much time I have for the gas exchange process, and our hardware systems has to be enough as responsive to give the proper response within the time limit. So that is what our the next phase, that how we are going to widen these concepts with the for the higher speeds, because this pumping loss and everything is mostly it is a main problematic at the low speeds. So that's why our first concept was to just prove it, that whether first of all it is possible, we can do that, and then once we have done it, then test it at the lower speed where we can have a more problem with the pumping power and everything.
Thank you for your presentation. And just to have an idea of the power you require, what is the holding effort you have nowadays in your system? With which effort can you hold close the valve?
So right now, this is the what in the presentations, it is just the air pressure. So air pressure. So right now we are dealing with a certain diameter of the actuators, and where right now whatever the experiments has been done and shown here, it is the air pressure is 3 bar.
Yes, but how much newtons do you use
So
to
that's what I told, that we know that area. So how much?
But I don't know.
This is another these things. Right now, anyway, I can disclose this experiment has a valve actuator has a diameter of the 50 mm. Sorry, 35 mm. So right now, what we are doing the optimizations in a different way. First of all, that what should be because packaging has the most important. We cannot have wide diameter of the actuators. So how much has to be the diameters, actuator diameters, because that is what it is going to depends the pressure and the force it is going to be, and it has to be the fast enough, because this is what, because if we are not going to precise very fast, then we are not going to, our system is not going to survive at very high speeds, because the response will be very less.
And why it's a springless system? It's a two-action system.
Yes. So this technology we did it with the springless event systems. That is another demerit of this first prototype of our systems. Now what we are developing, we are incorporating the springs also, because in spring when we are incorporating the spring, it has a both way advantages and disadvantages also. We need to create more force when we are going to have a forward motions, okay? But we are getting the saving the energy when we have the. In fact, we don't need any sort of energy when we are going to have the backward motions of the springs. So that both way is going to be played on.
Thank you.
Okay, so if we do not have any more question, we can thank the speaker. Thank you, Dr. Srivastava.
Thank you.
Long live India and France friendship.